Okay, so with this one we're going to take a look at a very simple circuit problem and applying Ohm's law and some of our rules, if necessary, to find out exactly everything that we want to know about our circuit. So I've got a very simple circuit here. I've got a battery or a voltage source. This one happens to be 9 volts. I've got it hooked up to a parallel circuit here with two different resistors. These are very low value resistors, so we're going to probably end up with a pretty high amperage, a pretty high current. But these are nice straightforward numbers, so it's not a bad representation of something kind of realistic. Although I probably wouldn't normally run something like this with this high of a current. Odds are good it would get very warm very quickly. Okay, so as I've recommended, when we're solving circuits, we want to make a chart with, I'm going to go with V equals I R. Got my 3 columns. And in this case, I've got only a couple of components to keep track of. 2 different resistors. So I need 1, 2 lines. So we're going to have, I can mark this guy A and this guy B. Never hurts to keep track of them that way. And so I'll do A, B, and total. That's for the entire circuit altogether. Now, when we're using the chart, we only go across the rows. We don't add up straight down or anything like that. So hopefully that won't be too confusing. But if you do a couple of these, you should get in the habit and it'll be something easier to keep track of. Now I've got a laundry list of things that I want to find out about this circuit. The first thing that I want to know is I want to find the total current coming out of the battery. Okay, well, let's go back to our chart. We've got our chart drawn up. Let's fill in information that we're given. Well, we know our total voltage is 9 volts. And we also know the resistance of A, which is 3 ohm, and the resistance of B, which is 6 ohm. Okay. Well, I want to know my total current. I want to find this guy, total, and then current. So for me to find that, with this reminding me that I want to use Ohm's law, V equals IR, I need to find this guy. Because I've got my voltage, so if I find my total resistance, then I can find my total current. Well, I can find my total resistance by finding out the equivalent resistance of these 2 resistors, or of all of my resistors in general, but in this case we've only got the 2. Well, these guys are in parallel, they're side by side, or more to the point, if I go through one of them, then it bypasses the other. I don't have to go through the other. Whereas if they're in series, if I go through one of them, I have to go through the other. That's a good way to find out whether it's in series or parallel. Alright, well these are definitely in parallel, and so if I want to find my equivalent resistance, Req, the equivalent resistance, again, is where we find out how these 2 resistors act together, and then we replace them with an imaginary 1 resistor that acts the same way. Since these are in parallel, we know that we find our equivalent resistance by 1 over our equivalent resistance equals 1 over our first resistor, which is 3 ohm, plus 1 over our second resistor, 6 ohm. Basically, we go through and we take the reciprocal of each of our resistances and we add them up that way. That's how we keep track of our equivalent resistance when we're dealing with parallel. Okay, well, I'm going to do this the old-fashioned way without a calculator, so I'm going to get the common denominator, which will be 6 ohm. So I'm going to have 2 over 6 ohm, that's nothing more than 1 over 3 ohm, plus 1 over 6 ohm equals 1 over my equivalent resistance. This comes up to 3 over 6 ohm. And so when I find my equivalent resistance, that's going to be Req equals 6 ohm divided by 3, which is nothing more than 2 ohm. Okay, so now I know my equivalent resistance for this whole thing, 2 ohm. I get to put that in. And now, because I have 2 pieces of information in this row, I can solve for the other. I can find the current through my total circuit is going to be 9 volts divided by 2 ohm. V equals IR. I want to solve for I, so I'll divide both sides by the resistance. And I find that my total current is 4.5 amp, which is pretty high. I probably wouldn't want to leave this plugged in for very long. Okay. Cool. So now I've found my total current, which was the first thing I was looking for, right here. We used our relationship with our resistors to find our equivalent resistance, the resistance of the entire circuit if we imagine it in a simple way. In fact, I'll redraw it over here. We've got our voltage source. I'm going to draw it kind of small though. And instead of having the 2 resistors in parallel like that, I found that when I combine them into one equivalent resistance, that equivalent resistance, how that one resistor would act, would be that it's 2 ohm. And that's still a 9-volt battery. Alright, so first part's done. Second part, I want to find out the total power consumed by this circuit. Okay, well, our equation for that, coming back over here, we have several equations, but the most common one was P equals, where P is our power, IV. PIV. Okay, where I is our current and V is our voltage across the component. In this case, for our entire circuit, our total voltage is 9 volts, and our total current is 4.5. So I'm going to plug that in. I'll have 4.5 amp times 9 volts. So I run these together, and I probably should have grabbed a calculator in this case because I'm feeling lazy. That'd be what, 45 minus 9? Oops. Yeah. Equals 40.5. It's too late in the evening for me to try and think too closely about this. Power, I should get units of watts. And, if you'll remember, an amp is equal to a coulomb per second. It's charge flowing per time. And a volt is equal to a joule per coulomb. So if I take amp times volt of coulomb per second times joule per coulomb, and I'll find that the coulombs cancel out and I'm left with joule per second, which is in fact a watt. So our units, I should say, work out. Okay, now one of the things that I'll bring up is I haven't filled out my entire chart, and I've gone through and I've started answering things, mostly because I filled in enough of my chart that I could answer the individual parts. It's not a bad idea to go through and fill out the whole chart, but if these were the only things that I was asking for, then that'd be doing a bunch of extra work, which isn't bad. It's good experience. But if you're taking an exam somewhere where you could use all the time you can get, then see what you can do and save the time on the other. However, on most exams, and most of the people who write them know this, they want you to show that you can solve all of this. They'll ask you for more things. Like I'm doing here, I ask for the current going through resistor A, the power being used in resistor A, and then the same thing for resistor B. So we're going to go through and we'll take a look at that. So we're going to have to fill these guys in anyway. Alright, well, we've got a problem. We know we've already used our trick with our resistances, right? We were able to add them together to get our equivalent resistance. So now there's a good bet, since we've used that one, we're probably going to look at our tricks that we have for voltage and or current. And the two things that we have are, of course, Kirchhoff's rules. For voltage, we have Kirchhoff's loop rule, and for our current, we have Kirchhoff's junction rule. Now, let's see what we can fill in. As to the junction rule, because I'm interested in current, right? That's the one that has the junction rule. Junction rule deals with current. Junction rule says whatever current I have going into a junction, into a little intersection, I have to have the same amount coming back out. We know that this guy was 4.5 amp. We solved for that. And so it goes into a junction right here. And so we know that 4.5 amps has to come out of that junction, but we've got two different paths that it can go along. And we don't really have a good indicator as to how much goes one way and how much goes the other. Okay, so going straight to the junction rule may not be the best approach on this. Let's try the other one. Let's try voltage, our loop rule, right? For the loop rule, on a closed loop, anywhere in our circuit, if we start from one spot, let's start here, right before the battery. If I go around it, I go through my battery, and my battery gives me plus 9 volts. I'm going to go through my battery, I'm going to come along here and go down through resistor A. I'm going to drop by whatever the voltage across A is, because whenever we go over a component like a resistor, it takes energy out. The battery gives us energy, that's why it's a positive voltage, and the resistor uses that energy, puts it into heat, light, that sort of thing. But it's going to take that energy out, and so that's why it's a negative. Okay? And then when I get to the far end of that, I come back, and it turns out I've got nothing else that I go through. I end up back where I started. So that's my closed loop. According to Kirchhoff's loop rule, that must come up to 0 volts. Okay. Well, 9 volts minus whatever our voltage drop across A equals 0. We know that our voltage through A equals 9 volts. We'd add that guy over to the other side, and we'd find that 9 volts equals our voltage through A. Now, we're keeping track of the voltage drop, the negative here. We've got that taken into account that it's pulling that energy out, and that really only comes into play when we're doing the loop rule itself. So when I plug it into my chart over here, I'm just going to put it in as a 9 volt value. Okay, so I know my voltage drop across A is 9 volts. Alright, now for A, I know my voltage and my resistance. I can solve for my current. 9 volts divided by 3 ohm should leave me with 3 amp. Okay, so now I've just found my current for resistor A. My current for A, I had sub 3 over here because that was before I actually labeled them as A and B. But my current going through there is going to be 3 amp. Or 3 amps. I can't remember what the proper plural is. I don't think it's terribly important. The next thing I want to know is the power consumed in resistor A. Well, I could do the same thing. I've got the whole thing filled in, so I'm just going to use PIV. P equals I times V, so I'm going to do 3 amp times 9 volt, and I'm going to end up with, what is that? That's 27? 27 watts. Alright, we've got that one done. Now for our final question. The current going through resistor B, the 6 ohm resistor, and the power consumed in that as well. Well, let's take a look at that guy again. Last time we had good luck using loop rule. Let's check what we get with that. Well, I start here, I get plus 9 from my battery, I go through the other guy, I have the voltage drop across B, and then I end up back where I started. Hey, it looks exactly like the other one. So, I have to have 9 volts that drops over it. So that's one way of doing it. The other way, let's use Kirchhoff's junction rule, right? We know now that we have 4.5 amp coming into this junction. How much is going through our resistor A? Well, I can check my chart. Right here, the current going through that is 3 amps. So I've got 3 amp going this way. So I have 4.5 coming in, 3 of it goes this way. What's that leave over here? Because what comes in has to equal what's going out. That leaves me with a current equal to 1.5 amp. 4.5 equals 3 plus 1.5. Alright, so I could cut out the middleman and just find that this is 1.5 amp, And that gives us a way of using Kirchhoff's junction rule. Of course, we'd see from the same thing that with our loop rule, we'd find that the voltage drop also has to be 9 volts, because I could do another loop, positive 9 from the battery, a drop down going through B, and then I come back and it has to be equal to 0, so it looks just like this. We'd end up with 9 volts there as well. And if we take 1.5 amp times 6 ohm, turns out we get 9 volts. So it works out. We've managed to double check our number. All right. So our current going through B, or the 6 ohm resistor, we found was 1.5 amp. And so our power through B is going to be equal to 1.5 amp times 9 volt equals, what's that going to be, 13.5? 9 plus 4.5, 13.5 watts. And you'll notice one final thing. The power that I'm consuming in A and the power I'm consuming in B, that's 27 plus 13.5. If I add up the powers that are consumed here, it equals the same power that is being supplied by the battery. Or, what we were saying, that's the power that's consumed by the total circuit. Well, this is the total circuit. We've only got the 2 resistors, so these need to add up to that anyway. Okay? So, that's going through and solving a very simple circuit, one with parallel, and it gives us some experience applying Ohm's law, Kirchhoff's loop rule, and Kirchhoff's junction rule. It also gives us experience with the chart that I highly recommend that you go ahead and make. Also with the chart, when you deal with extremely complicated circuits, if you don't know what to do next, you can just start looking at your chart and say, okay, what can I do to start filling in some of these numbers? Even if you get lost and you don't know how to get exactly what you're looking for, as long as you can continue filling in more and more of the chart, eventually you're going to have most of it filled in, if not all of it, and you'll be able to answer any question about the circuit.